Welcome to the Explainer. Today, we're taking a journey through the story of physics. But forget the dry textbook version. This is a story about revolution, about how we uncovered the fundamental rules of our universe. It's a tale of pure genius, deep mystery, and ideas that literally changed the world. Okay, so let's just dive right in. This story is all about revolution. I'm talking about moments where our entire understanding of reality got turned completely upside down, not just once, but twice. We started with a universe that seemed as predictable as a Swiss watch and ended up with one that is, at its core, fundamentally weird and uncertain. So, how did we get there? Well, our journey is going to follow four absolute giants of science who built, then broke, and then completely rebuilt our picture of the cosmos. Each one, stood on the shoulders of the person who came before, pushing us deeper and deeper into the fabric of reality. Let's get started. Our story kicks off way back in the 17th century with the one and only Isaac Newton. He gave us this incredibly powerful and kind of comforting idea that the universe is just a huge, predictable machine. A giant clockwork, you could say, where every single piece follows these perfect, unbreakable rules. Now, to build this clockwork model, Newton needed a new, more precise way to talk about the world. See, he realized some things, like temperature or mass, are just a number. That's a scalar. But other things, like a force or how fast something is moving, well, for those, you need to know not just how much, but also which way. And that's a vector. This might seem simple, but this distinction was absolutely crucial. So, with this new language in hand, he laid down his three legendary laws of motion. They're these elegant rules that describe, well, everything that moves, why stuff stays put or keeps going, how forces make things speed up or slow down, and that simple, beautiful idea that every push has an equal and opposite pushback. All of a sudden, the universe had a rulebook. And right at the very heart of it all is this one famous equation, F equals ma. Force equals mass times acceleration. And you have to understand, this wasn't just a bit of math. It was a philosophical bombshell. It meant that if you knew all the forces and positions of everything right now, you could predict the entire future perfectly. The cosmos was a solvable puzzle. For almost 200 years, Newton's clockwork universe was king. It just worked. But then, as we get into the 19th century, scientists started poking around at these invisible forces, electricity, magnetism, that just didn't seem to play by Newton's mechanical rules. And the biggest puzzle of them all? It was light itself. I mean, what is it? And how on earth does it travel through the complete and total emptiness of space where there's nothing for it to ride on? This one question was about to cause the first major crack in Newton's perfect machine. The mind-blowing answer came from James Clerk Maxwell. He realized that electricity and magnetism were really two sides of the same coin. And when he put them together in his equations, he found that they create the self-sustaining ripple that travels at, you guessed it, the speed of light. Light, he said, is an electromagnetic wave. And the craziest part, it doesn't need anything to travel through. It just goes. And all the experiments seemed to back him up. Light did all the classic things that waves do. You had interference, where two light waves could crash together and either get bigger or cancel each other out completely. And you had diffraction, where light waves would literally bend around corners. So for the physicists at the time, that was it. Case closed. Light is a wave. End of story. So picture this. It's around 1900. Physicists are feeling pretty good about themselves. The universe seems orderly, understood. Newton's clockwork is ticking along perfectly. And now they even understand light. But then, a really simple experiment, one that should have been totally straightforward, was about to blow the whole thing wide open. So the experiment is called the photoelectric effect. All you do is shine some light on a piece of metal and see if it knocks any electrons off. Now, the old school wave theory made a really clear prediction. Think about waves at the beach. A bigger, more powerful wave is going to hit you with more force, right? So a brighter, more intense light wave should knock electrons out with more energy. Simple. Logical. Except that's not what happened. Not even close. What they actually saw in the lab was baffling. It completely contradicted the elegant, proven wave theory. Physics had just hit a brick wall. Hard. And I mean, it was a complete and utter mess for the wave theory. Electrons just popped out instantly, no time lag at all. Weirder still, a really bright red light would do absolutely nothing. But even a dim blue light could knock electrons out. And cranking up the brightness, That just gave you more electrons, not more energetic ones. Nothing made any sense. Physics was completely stuck. The answer didn't come from just tweaking the old rules. It came from a completely radical new idea, something first hinted at by Max Planck and then fully brought to life by a young, unknown patent clerk named Albert Einstein during his miracle year of 1905. Einstein basically just threw the whole continuous wave idea in the trash. He said, what if light energy isn't spread out like a wave in a pond? What if it comes in tiny, concentrated little bullets of energy? He pictured light as a stream of these little energy packets, which we now call photons. And this is the absolute genius of it. The energy of one of these light bullets, or photons, is tied only to its frequency, which is basically its color, not to how bright the light is. And this one idea explained everything perfectly. Higher frequency blue light has higher energy photons that can knock electrons out with a bigger punch. A brighter light doesn't mean a bigger punch, it just means you're getting hit with more photons every second. The crisis was over, and the quantum age had just begun. So, after all that, a clockwork universe, electromagnetic waves, quantum packets, why does any of this matter to you? Well, because these seemingly abstract, kind of weird ideas are, and I mean this literally, the foundation of our entire modern world. Just think about it for a second. Newton's classical rules, that's why bridges don't fall down and why airplanes fly. Maxwell's amazing discovery about electromagnetism, that's the magic behind every radio, every cell phone call, the Wi-Fi that's probably connecting you right now. And Einstein's bizarre quantum idea about photons, that's the reason we have lasers. And more importantly, it's the reason the microchips inside your phone actually work. These theories are the blueprints of the 21st century. So that's our whirlwind tour through the story of physics. It's a story about being brave enough to tear down old, comfortable ideas to build new, more powerful ones. And it really leaves you with one last big question. 100 years after the quantum revolution, what fundamental rule about the universe are we completely wrong about right now? What are we about to discover next?